Let us explore gradient descent. This is an understanding of the fundamental optimization algorithm in machine learning. Gradient descent is an iterative optimization algorithm used to find the minimum of a function. In machine learning, we use it to minimize the error, also known as the loss function, by adjusting model parameters. You can think of it as walking down a hill. You look around, find the steepest direction downward, and take a step in that direction. Then repeat this until you reach the bottom. The update rule in gradient descent is represented by this formula. Theta is equal to theta minus alpha multiplied by the gradient of j of theta, where theta represents the parameters we want to optimize. Alpha represents the learning rate, which determines the step size. And the gradient of j of theta represents the gradient of the loss function. Here is a code snippet demonstrating gradient descent using number py. Define the function gradient descent, which takes in input features x, target variable y, initial parameters theta, the learning rate alpha, and the number of iterations. Calculate the number of training examples m from the length of y. Then, for each iteration, calculate the predicted values h by taking the dot product of x and theta. Calculate the gradient of the loss function. Update the parameters theta by subtracting the product of the learning rate alpha and the gradient. Finally, return the optimized parameters theta. There are three main types of gradient descent. The first one is batch gradient descent. This uses the entire data set for each update, which is computationally expensive but stable. It is best for small to medium data sets. The second type is stochastic gradient descent. This updates parameters using one random sample at a time, which is faster but has noisier convergence. This is good for large data sets. The third type is mini-batch gradient descent. This is a compromise between batch and stochastic gradient descent. This uses small random batches, balancing efficiency and stability. Let's explore some common challenges with gradient descent. The first challenge is learning rate selection. If the learning rate is too large, it can lead to overshooting the minimum. If it is too small, it results in slow convergence. Another challenge is local minima. The algorithm may get stuck in local minima instead of finding the global minimum. Another challenge is saddle points. These are points where the gradient is zero but not a minimum, causing slow progress. To optimize gradient descent, we can use momentum for faster convergence. To do this, we can use TensorFlow's keras optimizers.sgd, where we specify a learning rate, a momentum, and whether to use Nesterov momentum. We can also use adaptive learning rates by using optimizers like Atom, where we specify a learning rate and beta parameters. Modern optimizers like Atom combine adaptive learning rates with momentum to achieve faster convergence, better handling of sparse gradients, and automatic learning rate adjustment. Gradient descent has several real-world applications. Linear regression is used to find the best fit line for predicting house prices, stock values, or sales forecasting. It is used in training deep learning models for image recognition, natural language processing, and recommendation systems. It is used in classification for optimizing decision boundaries for spam detection, credit risk assessment, and medical diagnosis. It also has usage in reinforcement learning for training agents to make optimal decisions in gaming, robotics, and autonomous systems. Here are some best practices and tips for using gradient descent. Feature scaling is used to normalize features to similar ranges 0 to 1 or -1 to 1 for faster and more stable convergence. We can also use a learning rate schedule by starting with larger learning rates and gradually decreasing them during training. We can also use early stopping to monitor validation loss and stop training when performance stops improving. Finally, we can use k-fold cross-validation to ensure model generalization and parameter tuning. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.